Regarding scientists, this might be a name you heard of, Niels Bohr, for the Bohr model of the atom. But here we're going to describe the atomic theory of Niels Bohr in this DeBacco University video. All right, let's get into Niels Bohr atomic theory. Well, first off, as always, it's important to understand the context for which these scientists are living in when they're developing their theory. And Niels Bohr developed his atomic model around 1913. This is during periods of rapid progression in understanding of the atomic structure and emergence of quantum theory. This built on Rutherford's proposal of a dense positively charged nucleus back in 1911. Also, Thomson's electron discovery and Millikan's charge discovery with the neutron. So here we're taking in these previous models and we're starting to build on them. We're starting to get a little bit more of a refined idea, challenging what's being proposed and seeing if there's, quote, a better way or a new science that's showing some things. In the electrospectrum, again, scientists observe the elements that emit light at specific wavelengths, which neither Dalton, Thomson, nor Rutherford's models could really explain. So this is where Niels Bohr started to dive into this in a little bit more detail. Also, when we're looking at quantum theory, we're looking here at Albert Einstein's work coming basically publicly available, and this inspired Bohr to apply these quantum ideas to the atomic structure. And there's other mathematical formulas coming out at this time, so a great kind of culmination here and collaboration effort to work on refining the atomic theory. So Bohr's model, as again I said, you might be familiar with this, seen this, or heard of this. It's looking at this concept or theory of what we call orbitals. And this quantized electron orbitals are electrons that orbit the nucleus in fixed circular paths or energy levels. We can see that here. They are specific distances, each associated with discrete energy. So unlike Rutherford's model, where electrons can only occupy these allowed orbitals, preventing continuous energy loss, here we're looking at the ability for these electrons to jump between these energy levels, and this could explain how light is being emitted. So the breakdown of the general theory here, well, the nuclear structure is retained. So like Rutherford, Bohr proposed that atoms consist of small, dense, positively charged nucleus containing protons and later neutrons with Chadwick's addition and contribution, surrounded by orbiting electrons. And we get into the quantum transitions. Electrons can jump between orbitals by absorbing or emitting this quantum of energy, a photon, equal to the energy difference between levels. This helped explain the discrete spectral lines observed in elements like hydrogen. So when we get into kind of talking about light, we're jumping from this level to this level. That's going to emit a red wavelength. But from a higher level down here, we're looking at maybe a purple coloration. So this is explaining when these electrons jump from these different levels, the different colors of light that we see emitted, called spectral lines. In addition to Bohr's model, angular movement is quantized. Bohr proposed the angular momentum of electrons orbiting around the nucleus is basically quantified. He further added that electrons move only in those specific orbits. This rule is how he came up with the idea of orbits. Kind of like the concept of planets rotating around the sun, they have very distinct orbits. Hydrogen atom was the focus in Bohr's model, which was successful for hydrogen and allowed him to actually predict its spectral lines using a mathematical formula. This model used Millikan's electron charge and Thomson's electron concept to calculate the electron to nucleus interactions. So again, we see that further kind of contribution of science to refine the model. Now, how does this relate to the modern theory? Again, still we're talking 1913. But his modern theory uses these kind of this way to calculate orbitals in the sense that where are they most likely to occur. Uses a whole problems kind of statistics to generate that. So we get away from, on the modern model, these fixed orbitals to describe electrons, because this kind of creates a little bit of a limiting area, again called the planetary model. Regarding nuclear structure, the modern model does incorporate protons and neutrons with nuclear forces, which is explained by the quantum chromodynamics, which Bohr model really didn't address at that time. However, there's spatial accuracy here, where modern quantitative mechanisms explain fine structures. This is far beyond Bohr's hydrogen-focused model, but at least that was a good start. We're in chemical bonding, building on Bohr's idea that electrons determine chemical properties. Here we're looking at orbitals will overlap. We'll have ionic bonds, covalent bonds, so all of those can be further explained in this quantum framework. The modern model is fully quantum mechanical, replacing Bohr's semi-classical approach. But when we think about electrons and how they move, at least to initially understand them, this quantum planetary model is a great way to initially think about it, and allows us then, just like the scientists did, to further expand on this to start looking at electron clouds. So again, great start here, great way to develop, great way to still think about it today, but again, another contribution to the modern day theory.